So throughout this course, we're going to be looking at these different types of organic compounds. We just covered nomenclature of alkanes. We'll also be talking about physical and chemical properties of alkanes. Physical properties that we're most interested in are solubility and melting and boiling points. So in order to talk about these physical properties, we need to talk about some intermolecular forces. Alkanes are insoluble in water. They just do not mix with water. And the reason for this is that water is a polar substance and alkanes are nonpolar. Remember that the carbon-hydrogen bond, the electronegativities of these two atoms is similar enough that the carbon-hydrogen bond is essentially a nonpolar bond. So if you've got a hydrocarbon with only carbons and hydrogens, there's no way it can be polar. Just no way. Well, water molecules are very polar, and they are held together by hydrogen bonding. This is an illustration of hydrogen bonding. Water molecules, as we talked about in chapter 1, have a permanent dipole, a negative end and a positive end. Here's the electron distribution. This end's red and this end's blue. And so we have attractions between the negative end of one molecule and the positive end of another. And because this is hydrogen-oxygen bond, it's especially polar, and it's called a hydrogen bond. Okay, that's an intermolecular force. These guys just hold together. They're very strongly attracted to each other. It's a little bit like a clique in high school. There was that bunch of girls, right? And they were just so close with each other, you could not break into their social circle. So the alkanes, being nonpolar, they can't break in here. They get essentially excluded. And so alkanes and water just do not mix. And what we'll find is we can predict solubility of compounds in water by looking at their intermolecular forces, which come from how polar or nonpolar they are. Boiling point, oops, I skipped one. No, I didn't. Boiling point is another physical property that we're going to look at for each of these classes of compounds. Alkanes have lower boiling points than most other organic compounds for similar molecular mass. We're talking in generalizations here, and so we can compare two molecules that have a similar molecular mass. We can't compare a small molecule with a really, really big molecule and be able to predict anything about their relative boiling points. So alkanes are held together with van der Waals attractions. Depending on your, you all took chemistry before, or you wouldn't be in this class. Van der Waals forces get called many different things. London forces, dispersion forces, van der Waals forces, and also induced dipole forces. So hopefully one of those sounds familiar to you. Alkanes are not polar, but we can get a shift, a spontaneous shift of the electrons and get a positive on one end and a negative on the other, very, very temporary. Did I talk about this in chapter 1? No? Okay. I've explained it so many times, I just can't remember who I told it to. It's like my mother. She tells the same stories over and over again to everybody, right? So what happens is it's a little bit like a boat, you know, one of those blue and white cruises on the San Francisco Bay, and you go out and you tool around Alcatraz. And people are all over the boat looking around, and you go around Alcatraz, and the tour guide says, hey, look, here's Alcatraz, blah, blah, blah. And everybody goes to one side of the boat, right? And hopefully it's not overloaded, but the boat might list or tip just a teeny tiny bit, right? If all the people went to one side, that could happen, right? What can happen in a nonpolar molecule, those electrons are not fixed in position. They're moving all over the place. They can spontaneously well, actually they'd be over here with the negative. They can spontaneously end up on one side just by random chance. Got a bunch of things moving around. They could all randomly end up on one side. And when that happens, you get a partial negative charge. Well, that repels the electrons in a neighboring atom, which causes a positive. So it induces a dipole in the neighboring molecule. Now you've got a minus and a plus, and those are attracted to each other. But then the electrons here go back to being random, and this disappears. And so these van der Waals forces are very real, but they're very, very tiny. The reason they become significant is because they happen so frequently. And it's the only reason that, this is the only type of attraction that atoms have for each other, because an atom cannot be polar. And so nonpolar molecules have these forces of attraction. The forces of attraction get larger as the as the molecule or atom get larger. And the way I think of that is, okay, so I have 6 children. I told you that, right? Yeah, I've got 6 kids. I have a friend who has 1 child. So if we were both to take our kids to the zoo, my older 2 wouldn't want to go anymore, but if we were both to take our kids to the zoo, my friend with 1 child is going to know where that 1 child is all the time, right? Because she's just focusing on 1 child. Me, I'm probably going to have somebody running off to see the monkeys and somebody going to the reptile house. They're going to go in opposite directions, right? There's no way I can keep track of 6 of them and keep them all corralled, right? So a larger molecule has more electrons, and they're spread out farther, and so it's easier for them to get lopsided. And when they get lopsided, the charge is going to be somewhat larger. So larger molecules, more lopsided, more likely to lose track of their electrons, and the interactions are going to be stronger. These are called non-bonding intermolecular attractions. Intermolecular because they're between molecules. These are not chemical bonds. They're just static, well, not static, they're electrical attractions between different atoms and molecules. But they have significant effects on the properties of molecules. So we need to have an understanding of these intermolecular forces. And if this is all sounding very strange to you, you might want to go back to your Chem 3A notes and review that, because they did teach it to you. So what we see happen, here is an example, a table showing the boiling point of these alkanes as a function of the number of carbon atoms. So 2 carbon atoms would be ethane. Ethane boils at minus 100 degrees Celsius. And then we have propane and butane and pentane and hexane, and you get the idea. What happens to the boiling point as the number of carbon atoms increases? The boiling point increases. In order for a liquid to boil, the molecules have to get enough kinetic thermal energy to be able to break free from these attractions that are holding them together. Why is a liquid at all? Because there are attractions between the particles, and those are going to be the intermolecular forces. When it boils or evaporates, it breaks loose from those attractions and is able to go off into the gas state. So this demonstrates the stronger intermolecular forces that the larger atoms, larger molecules have. 10 carbon atoms is going to be a larger molecule. It's more easily polarized, and so those van der Waals forces are going to be stronger. We also see an effect with the branching. So here's pentane, which has 5 carbons. Here's 2-methylbutane, which also has 5 carbons. And here's 2,2-dimethylpropane, also has 5 carbons. These have the same molecular formulas, but the carbons are arranged differently. They are isomers of each other. Their boiling points are different. This one boils at 36, this one at 28, and this one at 10. And that has to do with the shape of the molecule. So here's normal pentane. It's relatively straight. And so what can happen, this is the ball and stick, and here are the molecular structures. This is the more branched one, the one at the bottom. So here we have condensed formulas. Here's the pentane. In order for the pentane to have intermolecular attractions to another pentane molecule, they have to get close to each other. Because these are relatively linear and pretty flat, they're straight, they can be straight, they can nestle up together and have really good contact. These are more spherical because of all the branching. And so here you've got one molecule and another molecule, and they can't have as much contact in between them. Another way to think of these intermolecular forces is they're like Velcro. And so if you have two objects that are covered in Velcro and they can lie next to each other, so they've got lots of surface area for the Velcro to contact, they're going to stick together more strongly than if you have some round balls and they can only touch their Velcro in a couple of little points, right? You've seen those Velcro bounce house things where you put on a Velcro suit and you bounce and you jump against the wall and you stick to the wall? I've never done one of those, but it looks kind of fun. How can Velcro hold your body weight, right? Your shoes keep coming undone. How does that work? Well, if you've got a lot of surface area, if you're wearing a Velcro suit and you've got your arms and your legs and your body covered in Velcro and you hit that wall, you have a lot of surface area and the force of attraction is going to be stronger than if you're only hitting it like maybe with your hands and your knees or something. Then you're not likely to stick. Does that make sense? Okay, so we'll be looking at these ideas of intermolecular forces throughout the semester because we're going to need to be able to predict, does this have a higher or lower boiling point than this other thing? And this is how we do it. We look at the shapes and whether they're polar or not. Any questions?